University of Verona. He wants to speak of weighting and counting, weighing and statistics and ontology in the old quantity.
First, let me thank the organizer for putting together this wonderful volume for having me here. It's really great to be here, to see friends, and it's really cool. And my contribution to the volume concerned kind of connecting part of the 19th century narrative concerning statistics and statistical ontology to the development in old quantum theory right before the Needle story actually started. And that's, so in the interest of time, of course I cannot give you more details, but this is basically the gist of my argument. This is famous quote from Sommerfeld: degrees of freedom should be weighted, not counted, therefore the title. And this is a quote that comes from, well, it's paraphrased from Schiller and kind of summarize the thought that were at that point about these mysterious things that were happening, applying Boltzmann statistics to the quantum physics. So, just some kind of philosophical preliminaries to start on the right foot as far as terminology is concerned. My big point is that one of the points is that statistical mechanics is crossed by sort of, well, ontological tension, right? It's statistical mechanics, so it's already in the name is a combination of two things. Now, here by ontology, I mean just a way to identify the theory's domain, right? What the stuff the theory is dealing with. So, if we take for granted that statistical mechanics deal with many particles, of course, you can look at the particles in two different ways. You can look at the particles as mechanical objects, which are, there are many of them, right? And also things that you treat statistically. So if you describe them as mechanical objects, they are very classically defined by, so described by Antonio mechanics. And in that case, they have an individuality, of course, which is warranted by the spatial-temporal continuity of their dynamical history. Right? They have a particle is something which is whose individuality is characterized by the fact that it has a unique dynamic history. And I call for short this deontology, dynamical ontology. And this is very, very Leibniz, basically. But of course, particles are also statistical entities, are things that statistics makes its magic with, right? And they are arranged in distribution, they can be manipulated, they swap them and do stuff with them. And in that case, when you treat them as statistical entities, of course, their individuality is warranted by the fact that they are different. that if you swap them, something changes from a statistical point of view, or doesn't, right? As you will see. And that I call this way of looking at the object from the lens of statistics, I call it the statistical ontology S. So, in brief, right, the ontology identifies particles in virtue of their dynamical history, of the fact that they have, as said, continuity, right, space-time. And from that point of view, individuality, identity is an intrinsic property, something that belongs to the particle. Statistical ontology instead identifies particles in virtue of the consequence of what you, what comes out from your statistical magic, right? And in that case, identity is kind of relational property. You need at least two particles to swap them. Now, one of the points that I made in the contribution and the repeat here is that in 19th century physics, the relation between these two souls, right, of statistical mechanics is kind of clear, right? It's a hierarchical relation, which you have the ontology, that the ontology comes first, namely statistical mechanics deals with mechanical particles, and sometimes, so they are distinguishable from this dynamical perspective, but sometimes, of course, for convenience, for formal reasons, you have to, we will see, do different descriptions. But the basic thing is that statistical mechanics deals with mechanical particles. Quantum theory, I will argue, changes this hierarchical relation, but to do this, well, it will take, it took a lot of time, and it took a lot of tension that was developed especially in 1910s when physicists tried to understand what actually Planck had done when he applied Boltzmann's statistical formalism to radiation. And quantum statistics stems out of this tension, and yes, we can call it creative tension, as Christian was suggesting, because again, it's, I think, an example of this exploring, right, of this trying to understand what is happening with formalism, conceptual tools, paper tools, if you want, or theoretical technology, as Warwick said. When you apply this formalism that physicists thought they had understood from 19th century physics to a different piece. So again, is an example, as Mila was saying, is an example in which formalism is coming dense with meaning. In this case, is ontological meaning, and the tedious process of exploring this meaning is actually what is at the foundation of quantum statistics. So this is just a plan. I will try to be quick and time. I will say something about what happens in the 19th century, so Boltzmann's statistical mechanics. Then I will say something about how Boltzmann stuff percolates into Planck quantum hypothesis. Then I also will be saying something about the roaring tents in which people explored both the radiation problem and the gas problem, which actually paved the way to Bose-Einstein. So some words about Boltzmann's statement. Right? Well, Boltzmann is very 19th century physics. Right? He is an example of what I would call the classical view, which means that he believed that statistical mechanics is about mechanical particles, which are individuals characterized by the fact that they have a unique dynamical history. And he is very explicit on that. In 1872 paper, famous paper on Boltzmann's equation, the H theorem, he compares at the beginning particles and individuals, very much in the statistical tradition of what, for example, Ian was describing, this avalanche of numbers, right? In persons, right? People. And even more explicit in the Principle of Mechanics, 1897, in which he plainly says that it's this spatio-temporal continuity that gives particles their individuality. So he is very much in this classical view, but also conceives that at times, for statistical reason, we might want to treat them also as non-individual. So basically, his idea is that the ontology comes first, and then sometimes you have to indulge in kind of statistical ontological magic. And Boltzmann's use of statistical models kind of reflects this view very clearly. I will just give you a couple of examples, well, famous examples that you might recall. The first example of Boltzmann's use of combinatorial statistical models is, of course, the 1868 paper in which he gives three different views or three different paths to the Maxwell-Boltzmann distribution. And towards the end of this kind of complicated paper, he gives this famous model. He considers a system of n particles as total energy E, then divides the energy in p intervals, right, not elements in that case. Magnitude is fixed but undetermined, it's epsilon. And then he says, well, we can calculate the Boltzmann distribution by through calculating the marginal probability for a particle, random particle, to have energy within a certain interval, right, between I epsilon and I plus 1. And of course, this is marginal probability, so it is proportional to the sum of the ways of distributing all the remaining particles over all the remaining intervals, and combinatorially calculates this using 19th century combinatorial theory, and the result is this number, which is equal to distributing n individual particles over p individual boxes. So that number will come back again. So just keep in mind two things. That number, well, I will remind you in due time, and the fact that here we are distributing n individual particles, right, distinguishable. I wouldn't use distinguishability because we saw that there is a contested concept of individual particles over p individual boxes. Then there is the other famous example, Gray 1877 combinatorial theory, which Boltzmann wrote, well, in response, not to real response, to the challenge. Anyway, in 1877, famous paper, we find three different combinatorial models. Two of them are probabilistically consistent, the other one should be discounted, but that's another story. And the first model is the famous one, right? The one that everybody knows because Planck also mentioned it. And it's a model that he makes vivid and clear using the Earn example, right? He assumes n particles whose total energy is divided into p elements. In that case, he uses these elements because he makes them Earn model, fixed magnitude, of course. And again, yes, it's not a division, distinction of energy. It's not a division of the energy continuing into intervals, but into elements. And then he gives this famous model, right, of Earn. So a Earn that contains a large number of tickets. Each ticket carries a number, which is between 0 and p. You can have 0 energy, p energy elements. Then he imagined that we make n drawings, of course with reintroduction, And at the end of end drawings, you get what he calls a complexion. Right? This is the first time he uses this word, complexion. Of course, most of the time, this complexion is an assignment of energy elements to particles. Right? Most of the time, it won't satisfy the energy constraints, so you have to discard it and then do it again. But at the end of the time, at the end of the process, you will get many complexions. And of course, complexions, in complexion, particles are individual things because they are individuated by drawing numbers. And each particle gets a number of energy element and so on. The complexion should be equiprobable and so on and so forth. Then comes the statistical part. If you swap energy between particles, you change the complexion, right? But you don't change distribution. That's the big point of the 1877 paper. So you can measure the probability P of the distribution counting the number of its complexions that are consistent with it. And it does that and calculates the normalization factor. The normalization factor, because of probability, normalization factor is the number of ways of distributing the P plus 1 tickets right over the particles. So all the way in which you can make this distribution. And here again, tickets are distinguishable, energy elements are not. This is precisely like the 1868 paper, the problem, and then it gets this number, again with J. Towards the end of the paper, he introduces another model, a model that is seldom commented upon, in which it does another thing, which is equivalent, but it's statistically different, or combinatorially different. He again assumes a urn that contains distinguishable particles, or individual particles. But here, instead of, it just draws particles, right? It makes P drawing, right? Again, with reintroduction. And then it defines the complexion no longer as the number of energy that one tickets to the particle, but it defines the complexion as the number, so any particle, each particle gets a number of energy elements equal to the number of ways in when it was drawn. Right. Advantage of this is this procedure automatically, of course, meets the energy constraints because you can't have a complexion that exceeds the energy, the total energy. But here the difference is in the statistical ontology. Why? Because the complexion here is defined, what counts is how many times, not which time, particles has been drawn. Right? So in that case, the P non-individual elements are distributed over n individual particles, and here he makes a calculation again for the normalization factor, which turns out to be remarkably similar to the one in 1868. So what it does is basically showing that the number of ways of distributing n individual particles over P plus 1 individual intervals is the same as the number of ways of distributing P non-individual elements over n individual particles. That has been commented by some historians, for example, Alexander Bach, years ago. It was commented as a sort of Boltzmann anticipating Bose-Einstein statistics, right? But Boltzmann doesn't comment at all on this idea. For him, it is just a formal curiosity, nice thing that statistics can do, right? But doesn't mean ontologically anything, right? Because the ontology is fixed by the mechanical nature of the particles, not by the fact that, yes, sometimes you can make statistical magic with it. Okay, then Planck comes and is very much more pragmatic, because Planck adopted what I call a kind of thermodynamic view on the relation between on physics and ontology, let's say, or kind of T ontology. It's been mentioned today a bit of this idea, right? Planck claimed very stubbornly that physicists should be primarily concerned with the macroscopic, observable properties of the system, and they should mess up with the micro level as little as possible. Right? Yes, sometimes we have to make some assumptions, right? But we should treat them with caution. Right? We shouldn't. Actually, we have to stick to the what we can observe, which is part of the thermodynamic tradition Planck belonged. This attitude was what allowed Planck to apply Boltzmann statistical tool in a way in a creative way, as I argue. Why creative way? Because, well, you know very well the story. Planck gets the correct radiation law by interpolating experimental data. Then he has to justify it, just cannot live with this interpolation, and use this combinatorial argument that he claims comes from Boltzmann, but is in fact adaptation of Boltzmann's statistical argument, a creative adaptation, because you suppose many resonators, many frequencies, calculates the way in which you can distribute resonators energy at a certain frequency, and then he makes the famous quantum move, in which he fixes the energy elements, and the probability of a certain energy distribution over certain species of resonators comes out proportional to this number that he claims comes from Boltzmann, because it is in fact in Boltzmann's 1877 paper, but it is in Both's model, and it is also in 1868 paper. Planck just refers to the first model. And we know that that number comes with two different interpretations, which historians recognize famously, right? You can interpret Planck's move as the distribution of non-individual elements over individual resonators, which was Martin Klein's famous thesis that Planck was already quantizing resonators, or you can read that number as the distribution of individual resonators over individual intervals, which was Kuhn's famous thesis that Planck wasn't in fact quantizing in 1900. The truth, I think, is that Planck simply couldn't care less about this, right? That Planck, because he's not committal to the deontology, to what happens in what is the stuff, the basic stuff that we can't observe, is very happy with both interpretation, because in fact he's focusing on the macroscopic level, right? So there is a kind of ontological fracture already in this foundational paper, which came from the fact that Planck had this kind of very non-committal attitude, right? Of course, that attitude wasn't shared by people which grew in the Boltzmannian tradition, like Ehrenfest, like Einstein, like Lorentz, who couldn't live with this very cavalier attitude of Planck about applying statistical tools. And here I will be very quick, just 5 minutes most. Yes, okay, great. And Planck theory was very accurate, we know, but was mysterious. And there were, right from the beginning, in the times especially, there were two different strands in investigating what the heck Planck had done with poor Boltzmann when applied to radiation theory. And one strand was studying radiation theory and the derivation of Planck's law, which is the strand that ended up in Bose, in fact. And especially Einstein and Ehrenfest were active in this strand. And then there is the other strand that is into quantum gas theory, which was a spin-off of Bose's paper, as we saw today. So I will be brief here and give an example of, well, kind of summarizing the tension in this Einstein versus Ehrenfest attitudes, right? Two different attitudes. Why? Because for Einstein, the big issue that Planck's theory carried with it is that it forces us to change our perspective of the individuality of microscopic entities, right? And it does that already in 1905, in which he supposed that the energy element can exist in a vacuum, which was already kind of ontological move that was way beyond Planck's original idea. Then it does again in 1909 when he introduced the fluctuation cavity radiation and the wave-particle duality. So for Einstein, the way in which we do statistical things with things is at least informative. We have to square it. We have to square these statistical formalism with the ontological commitment about microscopic level. So it is not just a formal trick or formal game. It has to. It tells us something, right? That is Einstein's strong thought in his investigation of radiation law. Ehrenfest instead, he was the keeper of Boltzmann's sacred fire, right? And he was very much in the Boltzmannian way of thinking. So for Ehrenfest, the big question was, what the heck Planck has done with Boltzmann, right? Which what we thought we understood that. Instead, he does strange things, and he very much assumes this classical view of the ontology. And then he tries to. His big question is which Planck's strange thing must tell us something about the kind of tricks that he did, right? Statistically, thank you, right? And we have to understand this, what he has done with statistics. And in 1906, you know, he showed that the quantum hypothesis is a sufficient condition for Planck's law. In 1911, he also saw that is a necessary condition, and especially the big result at the end of the 1811 paper is that he proved that Planck's quanta are statistically interdependent. And that was a big result for him, right? Because he finally understood what is the statistical trick that makes the statistical tools of Boltzmann work with the radiation theory. Planck has cheated, right? Has introduced this new thing. But there are no ontological consequences for it. It's just understanding what is going on from a statistical point of view. And then there is, of course, also the gas theory, which Daniela has already talked a little bit about, which I won't enter into. I just wrap up with a couple of take-home messages. Right? From a historiographical point of view, I think this story shows very much how the formalism comes with meaning, right? Comes with equipped with, in this sense, ontological assumptions that have to be teased out by just proving the formalism. Math is not that complicated, in fact, but the fact is that it's flexible as a conceptual tool, it's a paper tool, and sometimes it's difficult to find out how it works. There is no consistent research program. Again, it's 1910, right? People are just trying out. But there is not pure serendipity either. It's kind of constrained serendipity. So the emergence of quantum statistics is the result of this process of difficult navigation between statistics and ontology. And that is, again, right, kind of wrapping up. Boltzmann, for Planck for Einstein is more the way in which we use particles that must tell us something about what they are or how they behave deep down. For Ehrenfest is more the way in which particles are that should tell us how we use them, right, from a statistical point of view, and for particles for particles. Okay, thank you very much.
Thank you very much for
Right.
this paper. I feel sorry for it. You can't have one.
I see they speculate about the force of probability. But implicitly, which probability for me is classical.
Yeah. Yeah, well, Boltzmann used basically all kinds of probability. Most of the time he was using a frequentist definition of probability, right, in terms of how much time a particle stays in a certain region of the space. He sometimes uses a kind of Gibbsian probability, right, in terms of ensemble. Sometimes he used in 1877 paper, of course, he is using Laplacian probability. So he was very uncommitted about that. Planck is, of course, even less committed about it. He just uses this. Well, it's not correct. He also uses a kind of, at some point, he also uses a kind of Gibbsian ensemble.
Thank you very much.
You're welcome.